In this video, I introduce maximum causal entropy inverse reinforcement learning. Inverse reinforcement learning is used to find the reward function from the expert demonstrations. If the expert policy is not optimal, then we will have a policy degeneracy problem. That means one reward R will have multiple policy pi. Each policy pi will generate its own trajectories until reach the terminal state. So under this constraint, we train the model. We cannot show this R makes this learned policy close to the export policy. That's why we use maximum entropy to define the entropy loss function. Use this entropy loss function, we can pick up a trajectory with the maximum entropy. And this constraint train the model and get this R. This R can make this make sure this learned policy close to the export policy. Well, that's not all the story, because besides the policy degeneracy, we also have a reward degeneracy problem. That's why now we introduce a maximum causal entropy inverse reinforcement learning. The problem we are facing is very special because the data is sequential data. That means agent at the current state moves one step ahead, forward at each time. That means use this feature at, for example, agent at the state ST. When he takes action A, this A will be affected by the previous state and the current state and all the previous actions, not affected by any future state and actions. And in this way, we define the probability distribution of action A conditioned S. So we use this probability distribution to define this causal entropy. If this action, so the actions are IID, so we can use this sum of the probability at ST to express this probability distribution over the actions A conditions S, just states S. And then use this probability distribution, and we can define its causal entropy on this P, and substitute this sum in here. We take a log, and then we have this sum of the entropies. That's interesting because this entropy is not over all the trajectory. It's also not, is at a local, defined at a local, because whenever an agent moves one step forward, we will, from this point, look back, get a short sequence, and then we define entropy on this sequence. And whenever the agent moves one step, we get a 1. And we put all of them together until, this terminal state, we define this as the entropy over the states S over the trajectory. And use this way, we measure the uncertainty in causal conditioned distribution. That means use this way, we force the feature count and the learned policy close to the feature count and the export policy to reduce the uncertainty in the reward function. And then we use that entropy, causal entropy, as the loss function, subject to these two constraints that are same in the maximum entropy in inverse reinforcement learning. Here again, we for example, the agent adder here, whenever it moves one step, we calculate, we based on his short trajectory, we define entropy, and each time we can generate one entropy until reach the terminal state. We have so many entropies put together as the loss function. In this way, we can pick the trajectory with the maximum entropy, and we can reduce the uncertainty in the reward function. Here we compare the maximum entropy and the maximum Causal entropy, because this entropy is over the trajectory. So to find this policy, we only need the policy at the initial state. Here is different because whenever agent move one step, we need to calculate the policy. So we need to calculate the policy at each state. And this is in the backward path. In the forward path, that means the agent under the policy pi just propagates the signal from a current state to all the possible states along all the possible trajectories. So in maximum entropy, we just step by step, to all the possible next states. But here we need a short sequence. Each sequence we define entropy, and we put all the entropy together to get the feature count and run the policy. And then we compare with the feature count and the export policy to get the gradient of the loss function. And then we use this loss function to update the model parameters. For more details, please check with this reference. Thank you. Bye.